Okay, this is readiness check 5. Trim triangle for the Jetstar. We want to get the trim triangle so that its aft CG is 5% and the most forward CG at 0.737, elevator deflection minus 0.2. So let's see how we might go about doing this. Well, we're given the table, so we can do some preliminaries, answer some preliminary questions. They want to know the static margin when the Mach equals 0.2, and there's a table for that. And of course, if you go into the table, then that's going to be equal to minus Cm alpha over Cl alpha, which is 0.8 over 5, or minus a minus 0.8, or 16%, 0.16. And we know that that equals, KSM equals X AC minus X CG. And so if the CG is given at 0.25, that means that the aerodynamic center would have to be after that, so it would be 0.41. So XAC so XAC would equal 41%. If you climb to 40,000 feet, so at 40K, at 40,000 feet, the aerodynamic center is going to be the same. So that will be the same. But the derivatives change. So the static margin, again using the same formula, Cm alpha over Cl alpha equals minus a minus 0.72 divided by 6.5 Cl alpha, and that equals 0.11 or 11%. And again, that equals X AC minus X CG. But since the aerodynamic center is the same at 41%, that means that the X CG would be 30%, or 0.3. 30% and then 0.41 would give you the aerodynamic center at 41%. So these are the preliminaries to doing the trim triangle for this problem. So for the trim triangle, we're given that C sub L is 0.74. That's from the table, or 737. No need to go to 3 decimal places here. And once again, the static margin is minus Cm alpha over Cl alpha, and they're both given as minus 0.8 and 5. So you get 16% for the static margin. So we can plot that starting from 0.16 and going to 0.74. 0.74 should give us a line that looks something like that, where our C sub L at 0.74. Now an aft slope of 5% is going to drop one of these boxes. It's going to drop one of these boxes here as I go C sub L to 1. So that should give us a line that looks something like so. And the forward CG has to allow us to land at a delta E max, which is given to be minus 0.2 radians. And we know that from the table that Cm delta E is equal to minus 0.81. And since I don't know anything about the landing static margin, then I will assume this is equal to Cm delta E bar as a first cut. So let's make that a first cut. In actuality, Cm delta E bar equals Cm delta E derivative plus KSM, which would be forward this time, times CL delta E. We have CL delta E, but I don't know what the static margin forward is yet. So as a first cut, you can just use this approximate equality to give a first cut. Certainly on an exam, that's what you'd want to do. So if you multiply CM delta E times delta E max, you'll get 0.16. So the forward CG is going to look like this line, and its slope, this slope is going to be 0.16 plus 0.27, so that's 0.43. So the slope of this KSM is going to be 43%. So the difference in slope will be from 16%, which was this static margin, to 43% forward. So if we apply our fundamental formula, then we know that our KSM, which will be 0.43 or 43%, equals our XAC. Our XAC is at 41%, so that's at 4.1. So this is KSM forward, and that's XAC, minus what we need to find is the center of gravity position. And if you solve that, you'll see that your center of gravity, is going to be equal to minus 0.02. It'll actually be ahead of the datum plane. Okay, so the CG will move ahead of the datum plane, or you could use 0. Now, to make the trim triangle, we take the difference between the 16%. If I want to draw the trim triangle, then the aft CG, which we see goes from 16% to 5%, that 11% of going aft will start at the origin, and the 11% should look like so. So this would be the trim triangle. That's the trim triangle aft CG. The forward CG on the trim triangle will be going from 16% to 43%. So that's a 27% change. So a 27% change would look like so. So I have 27% aft and 5%, or 5% aft and 27% forward. And then you'd have to map the stall line, which I did not do. I didn't give you a stall. So you would have to pick a stall line wherever you thought it might occur, and you could plot alpha stall, 0.2 or 0.3 radians, onto this curve from your you get extra credit if you did that. But anyway, you'd have a stall line that would probably go something like so. And so when you finish the trim triangle, it would end up looking like so. So your trim triangle would be, your aircraft would be able to be anywhere in trim inside of this triangle, and this would be the stall line. And that would have gotten, if you put extra credit for the angle of attack, which I'm not going to do, but make sure you know how to do this trim triangle. Okay?